We know that the capital F prime of x represents the rate of change of y equal to f of x with respect to x. F of b minus f of a is the change in y when x changes from a to b. Now, although y can change in any direction, f of b minus f of a represents the net change in y. So this brings us to the net change theorem, and this states that the integral of a rate of change is the net change, and it's written as the integral from a to b of f prime of x dx, which is equal to f of b minus f of a. So this simply looks like the fundamental theorem of calculus part 2. Now, for example, if an object moves along a straight line with position function s of t, then the velocity is equal to v of t equal to s prime of t. So we can say that the integral from t1 to t2 of v of t dt is equal to s of t2 minus s of t1. Now, this is the net change of the position, or another way to call it is the displacement of the particle during the time period from t1 to t2. However, if you want to calculate the total distance, then we'll have to do something different. So this means that the object travels during the time interval. We need to look at the intervals when the velocity is greater than or equal to 0, so when it's moving to the right, and also the interval when the velocity is less than or equal to 0, when the particle is moving to the left. So in both cases, the distance is computed by integrating the absolute value of the velocity, which is then the speed. So therefore, we are going to get the integral from t1 to t2 of the absolute value of the velocity, dt, to give us the total distance traveled. So geometrically, here is what it looks like. So let's say that our x-axis represents the time and our y-axis represents our velocity. Then the area under the curve, or the area between the curve and the x-axis, will be our distance. So this is A1, A2, and A3. So when I want to calculate the displacement, I'm going to look for the integral from t1 to t2 of my velocity. So that's going to be A1 minus A2 plus A3. So notice that the displacement is the net change of the position. So it's calculating how far it has moved. The distance is another way to say the total distance. We're going to be calculating the integral from t1 to t2 of the absolute value of the velocity. So this time we're going to go A1 plus A2 plus A3. So although I use the word distance to talk about displacement, it's actually talking about where do we end up after all this time. Whereas the distance is, what is the total distance I've traveled, moving left and right. So when I integrate velocity over an interval from t0 to t1, it will produce the change in the value of the position as t increases from t0 to t1. So this is written as the integral from t0 to t1 of the velocity dt. Or we can also change the velocity to s prime of t, because we know that velocity is s prime of t. So when we look at the integral this way, we have the integral from t0 to t1, s prime of t dt, which is actually equal to then s of t1 minus s of t0, which is the displacement or the change in the position. So if a particle is moving horizontally, the displacement is going to be positive if the final position is to the right of the initial position. Displacement is negative if the final position is to the left of the initial position. So if we draw a diagram, this would be our t1, and then this would be our t2. In the second diagram, we would have t1 here, and then the time t2 would be to the left. So this is, we're talking about not t2 in terms of it going to the right, but where we would end up. And third, displacement is 0 if the final position is the same as the initial position. So let's take a look at some examples that apply these ideas. So we have a particle, and it moves so that at any time t greater or equal to 1, its acceleration is given by a of t equal to 1 over t squared plus t. At a time of t equals 1, the velocity is also given to be negative 2.5 meters per second. So I want you to find the velocity for time greater than or equal to 1. So in order to find our velocity, we need to integrate our acceleration. Now, to help you integrate this, it might be easier for you to think of 1 over t squared as t to the negative 2. So when we do that, we have t to the negative 1 over negative 1 plus t squared over 2, and then plus c. So now what we're going to do is we're going to use the information that at a time of t equals 1, it is negative 2.5 meters per second to find our c value. So we're going to plug in 1 for t. And moving all the numbers to the right side, we get c is equal to negative 2. So our velocity will then be negative 1 over t plus t squared over 2, and then minus 2. So what I want to do next is to find the displacement, and then show you also how to find the total distance so that you can see the difference. So to find the displacement, we need to find s of t, and we're going to integrate from 1 to 4 the velocity function. So that's going to be negative the natural log of 4 plus t cubed. Now, since the exponent is going to be 3, we're going to go 2 times that 3, so that will be 6 in the denominator, minus 2t from 1 to 4. So we're going to substitute 4 in first. So we get negative, oh, sorry, I made a mistake. I kind of did that ahead. So this should actually be t inside here. So this will be the natural log of 4 plus 4 cubed over 6 minus 2 times 4, and then minus, and then the natural log, negative natural log of 1 plus 1 cubed over 6 minus 2 times 1. Okay, so simplifying these numbers, we get negative natural log of 4 plus 64 over 6 minus 8. This natural log will be 0. So we have minus 1/6 and then plus 2. And simplifying all the numbers, we get 9 over 2. So negative natural log of 4 plus 9 over 2. And then to get a decimal answer, we plug it in to get 3.114. And that's going to be in meters. So let me show you the difference with the total distance. So in order for us to find the total distance, we need to set our velocity equal to 0 so that we know when the particle is going to be stopped, and then when it's moving left and when it's moving right. So we're going to set our velocity equal to 0, and then we're going to solve for t. So I'm going to multiply everything by 2t first to get rid of our fraction. And then let's write our function in descending degree order, or our equation. Now, in order for us to solve this, I actually need to use my graphing calculator. So I'm going to get 2.214 for my time, and that's with a graphing calculator. So when we do this, we know that's the time where it stops. So we are going to integrate. So what we're doing now, actually before I use this number, what we're trying to do is find the total distance. So really what I want to do is integrate from 1 to 4 the absolute value of negative 1 over t plus t squared over 2 minus 2 dt. Now that I found out where the velocity has stopped, I know that I need to integrate from 1 to 2.214, and we're going to take the negative of this function, dt, plus 2.214 to 4 of negative 1 over t plus t squared over 2 minus 2 dt. Now, the reason that I know that this part is negative is that when I plot my 2.214 number, I can check my velocity, and I know this is negative and this is positive. So therefore, that's why I need to take the negative of this absolute value and then the positive of that absolute value. So just to speed things up, I'm going to substitute and use my graphing calculator in the integral notation or integral function on my calculator to calculate 6.275 meters. And this makes sense because you can see that the total distance is greater than my displacement. Now, finally, what I want to end with is just to show you some other applications of the net change theorem. And it can be applied to other areas in the natural and the social sciences. So, for example, if C of t is the concentration of the product of a chemical reaction at time t, then the rate of reaction is the derivative dc dt. So we have the integral from t1 to t2 of dc dt, and this will equal c of t2 minus c of t1. So what this means that this is the change in the concentration from a time of t1 to t2. So important that you know what the c and the t stand for. And if it gives you the units of measurement, you should include that as well. And the second example, if the mass of a rod measured from the left end to a point x is m of x, then the linear density is, and this is a rho, the Greek letter rho, so rho of x equals to m prime of x. So this means that if I integrate from a to b of rho of x dx, that will give me m of b minus m of a. And this stands for the mass of the segment of the rod that lies between the points x equals a and x equals b, measured from the left end. So here are some examples, and you can look at in your textbook for some other applications of the net change theorem.